and welcome to this series of lessons on electromagnetism. As you might remember, we have studied magnetism and electricity before, but these topics were considered separately. At one time, people didn't think there might be a relationship between electricity and magnetism, but then in the early 1800s, scientists began to look for links between them. Think back to all the ideas you've heard about electrostatics and magnetism. The one idea that links both of these topics is the concept of a force field. Let's recap what we mean by this idea. Around any magnet, there is a region of space where the magnet can exert a force on magnetic materials even though there is no contact between the magnet and the objects. This region is called a magnetic field. We can determine the shape and size of the magnetic field by using iron filings. Here you can see how the iron filings, which have magnetic properties, experience a force from the magnet and line up with the magnetic field. Another way to show the magnetic force field of a particular magnet is to place a series of free-moving magnets around the magnet. Normally, a compass points in the direction of the Earth's North Pole. Free-moving magnets are found in plotting compasses. When you place these compasses near a magnet, these little compass needles all behave a bit differently. They experience a force of attraction or repulsion and so point in the direction of the magnetic field of the bar magnet, not to the North Pole of the Earth. Can you see how that near the North Pole end of the bar magnet, the compass needles are repelled by the magnet, and at the South Pole end, they experience attraction and point towards the magnet? To show this magnetic force field, we draw in the field lines around the bar magnet. We show the direction of the field as going from the North Pole of the magnet to the South Pole. We use arrows to show the direction of the force on the free-moving compass needles. Remember that field lines never cross each other. Also, where there are many field lines close together, the magnetic field is strong, and where the field lines are far apart, the magnetic field is weaker. Now I need you to think back again to what you know about the electrostatic force field. You can probably remember learning that there is an electrostatic force field around charged objects, but let's recap this idea just in case. When a positively charged metal conductor is placed in a flat dish of oil containing small seeds, the seeds spread out to show the electrostatic force field pattern. This is because the seeds are insulators which can hold a charge, and because they are charged, the seeds experience a force due to the electrostatic force field. We draw diagrams using field lines to represent the electrostatic field. In the case of an electrostatic field, the direction of the field is shown as the direction of the force applied to a positively charged point charge placed in the electrostatic field. In other words, the electrostatic field is shown by the direction in which the seed line up. Remember, magnetic fields and electric fields are not the same. Magnetic fields exert a force on magnetic materials, like the iron filings, while electric fields exert a force on insulators that can hold a charge, like the seeds. Let's take a look at another example of this very important rule. A free-moving magnet will be affected by another magnet, but will not be affected by a charged rod. This is because all free-moving magnets will be affected by a magnetic field, but not by an electrostatic field. A free-moving charged PVC rod will not be affected by a magnet, but will be affected by another charged PVC rod. This is because all free-moving charged objects will be affected by an electrostatic field, but not by a magnetic field. So far, we have thought about the links between static electricity and magnetism. But what about current electricity? In electrostatics, the electric field surrounds stationary charges. But what happens to the electric field when the charges are moving in a conductor? Well, in 1820, Hans Christian Oostert noticed a strange effect of a moving charge during a lecture demonstration. At the time, Oostert was using a chemical cell as a battery and was passing electric current through a platinum conductor, which he was trying to get to glow brightly. He also had a free-moving magnet on his desk. He noticed during the experiment that every time an electric current passed through the conductor, the magnet moved to a new position. When the electric current was turned off, the magnet returned to its original position. Oostert had made a major discovery in front of his students. The charges moving in the conductor had created a force field that affected a free-moving magnet. Now, we all know that the only thing that can affect a free-moving magnet is a magnetic field. So we can conclude that a charge moving through a conductor produces a magnetic force field. Oostert's discovery showed the first link between current electricity and magnetism, and it is this link that we are going to explore in this series of lessons. In this lesson, we will investigate the relationship between the electric current in a conductor and the magnetic field around the conductor in more detail. By the end of this lesson, you should be able to draw a diagram to represent the magnetic field around a straight current carrying conductor. Right, let's get started with the experiment. To begin our investigation, have a look at the apparatus I have here. I have a piece of copper wire that passes through a piece of stiff cardboard at right angles to the cardboard. These small plotting compasses can be placed on the cardboard around the copper conducting wire. Notice that I have placed the compasses in concentric circles. Next, I have connected the copper wire in series with a variable resistor to regulate the current passing through the conductor, an ammeter to measure the current, and a power supply. Now I'm going to turn on the power supply, and you need to look carefully at what happens to the compasses. What did you see? Let's look at that again. Notice that when the power supply is switched on, the compass needles together form concentric circles around the conductor. The compass needles remain in their new positions while charge flows through the conductor. What do you predict will happen when the current is switched off? Let's see what happens. When the current is switched off, the needles return to their original positions, pointing to the Earth's North Pole. I'm sure you'll agree that this is very clear evidence that a current passing through a conductor produces a magnetic field. The magnetic field around a current-carrying conductor is the same as the magnetic field around a magnet, but there is a difference. For a bar magnet, the magnetic field is always present, but the magnetic field around the conductor only exists when electric current is passing through it. We call this a temporary magnetic field. As with the other fields, we need to be able to represent the temporary magnetic field in a diagram. We draw the diagram to show the field lines around the conductor. In the diagram, we take a cross-sectional view of the conductor and so represent it as a small circle. Now have a careful look at the arrangement of the compass needles again and see if you can draw the field line pattern in this case. I have drawn my first field line as a circle around the conductor. This represents the first group of compasses closest to the conductor. Notice that the compass needles point in an anti-clockwise direction, so I have added in the direction of the magnetic field on my diagram. The second field line corresponds to the next group of compasses that are further away from the conductor. They also point in a circular pattern and in the same anti-clockwise direction, so I can draw in a second circular field line. This diagram represents the magnetic field at one point along the conductor, but the field has the same shape and strength all along the length of the conductor. Scientists use the symbol B to represent the magnetic field and measure its strength in units called Tesla T. Remember, when a magnetic field is strong, we draw in the field lines close together, and when a magnetic field is weaker, the field lines are drawn further apart. Let's label these ideas in today's task. Draw diagrams to represent a strong magnetic field and a weak magnetic field forming around a straight conductor. In our next lesson, we will investigate what factors affect the magnetic field formed around a conductor. Till then.
Yeah.